Alright, the goal of this lecture is to prove a theorem that is called the contraction mapping principle, also known as Banach's fixed point theorem. So the theorem goes like, let X be a Banach space. And S is a subset of X, which is non-empty. Okay. And we have a mapping from S to S. So given those conditions, if this mapping is a contraction, then there exists a unique fixed point of F in S. So this is the theorem, but there are a bunch of technical terms we need to understand in order to understand what this means. Okay, first of all, we need to understand what a Banach space is, and what is contraction, and what is a fixed point. So we will going to define these notions in turn. Alright, first we need to define the notion of the norm. Okay, I assume you already know something about the vector space. So here's the definition of the norm. Okay, let X be a vector space over the field K. In practice, this field K is either real numbers or complex numbers. Okay, and the function we write like this: from X to real numbers is called is a norm if it satisfies the following conditions. So first, for all elements of X, so for each vector, we have its norm is greater than or equal to 0. Okay, and in particular, if the norm is 0, actually the norm is 0 if and only if this vector is 0. Okay, so don't get confused. This is a real number. Okay, this is a vector, 0 vector. Okay, so this is a real 0 as a real number, and this is 0 vector. Okay, so the norm is 0 if and only if the vector is 0. And the second condition, for all alpha in K, so that's a scalar, and u in X, we have alpha u's norm is modulus absolute value of alpha times the norm of u. So it's kind of linear operation, but it's not really linear, but we have absolute value here. Anyway, and the third condition, for all vectors u and v X, we have this triangle inequality, u plus v, its norm is less than or equal to the sum of their norms. Okay, so I think you are already familiar with this norm. In fact, in vector space, this is usually called the length of a vector. or length or magnitude or the modulus of a vector. So it's actually a norm. And the next definition is the norm space. Okay, so if we have a set X, it's actually a vector space, and if we have a norm defined on it, then it's called a normal space. Easy. And if we have a norm, we can define a distance. So if we, let's say, we have two vectors, and we can define the distance between two vectors as the norm of their difference, right? So the distance here is 0 if and only if the two vectors are identical, right? So this is because of the first axiom of the norm, this one, right? So a norm is 0 if and only if this vector is 0. So in that case, in this case, so u minus v is 0. So that means u is equal to v. So in this way, we can define a metric in this space. If we have the distance in a space, then we can think about convergence of a sequence. For example, if we have a sequence like this, a1, a2, and so on, and these are in this space X, normal space X, then we can consider its limit as n goes to infinity. For if it converges to something, then we say it converges. So what does it mean? So it means, so as usual in the case of sequence of real numbers, for any epsilon which is positive and real, there exists some natural number such that for all natural numbers, if this lowercase n is greater than uppercase n, then the distance between an and alpha is less than epsilon. So if this holds, then we say this sequence an converges to alpha. Okay, so in this case, this sequence may not be just sequence of real numbers. It can be sequence of vectors. So this is any set on which a norm is defined. So we can apply this notion of convergence of a sequence to a more general space. And similarly, we can define the notion of a Cauchy sequence. Just like the sequences of real numbers. So this means Cauchy sequence means if we have a sequence, then the difference converges to 0 as m and n go to infinity. So if this is the case, then the sequence is called a Cauchy sequence. Now, if we have a space, a normal space, X, and if every sequence in X, every Cauchy sequence in X converges, then we say this space X is complete. Complete if every Cauchy sequence in X converges. Okay, now we have the definition of Banach space. So this is nothing but a complete normed space. So it's a complete normed space. So Banach space means it is a vector space and it has norm and it is complete. At this point, let us prove a little lemma. So lemma. It's about absolutely converging series and completeness. So let X be a Banach space. And suppose we have a series like this, x1 plus x2 plus and so on. So this series converges if it is absolutely convergent, which means if the sum of absolute values, I mean the norms, is convergent. So if this is finite, okay, so this is the lemma. So let's prove it. Let's see. First we define this finite sum. Let Sn be x1 plus x2 plus up to xn. Okay, and suppose m is greater than n. M and n are both natural numbers. Okay, then the norm of Sm minus Sn is the norm of sum of x k's from n plus 1 to n. And using the triangle inequality, we have this is less than or equal to the sum of the norms of each term. Okay, and by assumption, so we're assuming this. So this when n and m go to infinity, then this should converge to 0 because this infinite series is finite. So this, if both n and m, if they go to infinity, then this converges to 0. Otherwise, it will not be finite. Okay. So as m and n go to infinity, so this means, therefore, Sn, this is a Cauchy sequence. So now we are assuming that this space is a Banach space. So these x1, x2, these are elements of this Banach space. So since Banach space is by definition complete, therefore this sequence converges in this space. That means this limit, this series converges. And we are done. Next, we give another definition, which is a fixed point. Let's say X is a set and C and D are subsets of X. And let F be a mapping from D to C. So D is the domain of F and C is the codomain of F. Now, if x in x, actually it should be in D, is set to be a fixed point if we have x equals to f of x. Okay, so it is called fixed point because if we put x in this fixed point of f, by the way, so this x doesn't move, right? If we plug x into this mapping, then we get x. So this x can be again put into the mapping f, then we get the same result. So it doesn't move. That's why it's called a fixed point. Next, we define the notion of contraction. So let's define it. Contraction. Okay, so let X be a normed space. Normed space. And C and D are subsets of X, and F is a mapping from D to C, let's say. Okay, and this mapping is said to be a contraction mapping. Contraction mapping, or simply contraction. If there exists a real number between 0 and 1, including 0 and excluding 1, so it's less than 1, positive, non-negative, and less than 1, and such that for all x1 and x2 in the domain of f, we have this property: f of x1 minus f of x2. If we take the difference and the norm, then this is less than or equal to r times the norm of the difference between x1 and x2. Okay, so this means if we apply the mapping f to x1 and x2, then the difference is smaller than the difference or between the original x1 and x2 before application of the mapping, because this r is less than 1, so this is smaller than this norm. So in a sense, if we apply this mapping f, then the difference between 2 points becomes smaller and smaller. So that's why we call it a contraction. Now we can actually immediately see that any contraction mapping is continuous. Okay, so let's summarize this as a lemma. Let's say any contraction mapping is continuous. So if you remember the definition of continuity, it seems almost obvious. So to prove this, for any epsilon which is positive and real, if x minus x prime is less than epsilon, then f of x minus f of x prime is less than or equal to r times x minus x prime norm, right? Because this f is assumed to be a contraction, right? So there exists some real number which is between 0 and 1, not including 1. This holds. So this is because of contraction. Contraction. And now, since we are assuming this is less than r epsilon. But this is less than epsilon because r is between 0 and 1, not including 1. So this means for any real number, positive real number epsilon, we have this if we choose x and x prime to be close enough. Therefore, f is continuous. And we are done. With all these preparations, we can now prove the contraction mapping principle. So it's a contraction mapping principle. So let X be a Banach space. And S is a subset of X, which is not empty. And we have a mapping F from S to S, which is a contraction. Contraction. So these are all assumptions. Then there exists a unique fixed point. Point of f in S. Okay, so there are actually 2 points. There exists and it's unique. Okay, so we need to prove each of them. First, let's prove the uniqueness. Okay, that's easy actually. So prove. First, we prove uniqueness. So to prove uniqueness, suppose x and x prime in S are both fixed points. Of f. Then we have x equal to f of x and x prime equal to f of x prime. So because they are fixed points. Now, therefore, we have x minus x prime norm is equal to f of x minus f of x prime norm. Right. And since f is a contraction, then we have some real number between 0 and 1, r, which we call r, such that this holds. Right? Because f is a contraction. So therefore, if we move this to the right-hand side, left-hand side, we have 1 minus r x minus x prime norm less than or equal to 0. However, this r is between 0 and 1, so this is positive and this is positive, so it is actually greater than or equal to 0. So since 1 minus r is not 0, we can, and it's positive, So we can divide everything here by 1 minus r. That means 0 is less than or equal to the norm of this difference between x and x prime, which is less than or equal to 0. So this means x is equal to x prime. This is 0, this is 0. So actually all of them must be, so this must be equal to 0, which means this. So the uniqueness is proved. Next, we prove the existence of a fixed point. Take any x0 from S. Okay, then we define a sequence x1, x2, and so on by this recursive formula. Xn equals to f of xn minus 1. N is 1, 2, and so on. Okay, so this is just anything as long as it is in S. So we pick an initial value arbitrarily, then define the next value by applying f. So we repeat this over and over. Okay, and clearly, because the codomain of f is S, so we have for all n natural numbers, xn is an element of S, which is both the domain and codomain of the mapping F. Next, we have we take this difference xn plus 1 minus xn. Okay. Now, this is by definition, xn plus 1 is f of xn, and xn is xn f of xn minus 1. But f is a contraction, so there exists some r such that we have n minus xn minus 1, right? So r is a real number between 0 and 1. So if we repeat this process, then eventually okay, let's try to see the next step also. So if we do this again, then we have r squared times xn minus 1, xn minus 2, and so on. So eventually we have r to the power of n times the difference between x1 and x0. Okay. Now, note, we have xn plus 1 is xn plus 1 minus xn plus xn minus xn minus 1, and so on, and x1 minus x0 plus x0. So this is sum, let's say k from 0 to n, xk plus 1 minus xk plus x0. Okay, why are we doing this? Okay, so if we take, let's see, so if we take the norm of both sides of this equation, we have xn plus 1 norm is, and applying the triangle inequality, we have this is less than or equal to the sum of this right? But now for each of these terms here, we can apply this inequality. Okay, so this means this is less than or equal to this r to the power of k and x1 minus x0. But this is a constant. And so apart from this constant, this is just a geometric series. Okay, so this is, okay, so let's write it again. And after all, this is less than or equal to x1 minus x0 norm over wait a minute, x1 minus x0 over times, let's see, 1 minus r to the power of, what is it, n plus 2, I guess, 1 minus r plus x0. And this converges to, so since r is between 0 and 1, this will converge to 0. So after all, we have x1 minus x0, 1 minus r, x0, which is obviously finite. So if you remember a previous lemma, then this indicates that this summation, okay, just a moment. So xn plus 1 was this summation, right? K from 0 to n, x k plus 1 minus xk. So this this converges. So this is a summation. So if we take n to infinity, then this converges as n goes to infinity, because this is finite, right? So therefore, this means this limit exists. Okay, so let's define this limit as x star. Okay, now we have by definition xn plus 1 is equal to f of xn. Now for both sides, if we take n to infinity, then since f is continuous, because it's a contraction mapping, so it's continuous. So therefore we have x star equals to f of x star. So this x star is a fixed point. Actually, it's unique, so we can say it is the fixed point. Okay, we should write, since f is continuous as n goes to infinity. So now we have proved that that a fixed point exists, and we are done.